Hello, everyone. Welcome to our webinar today. My name is Justin D'Souza. I'm a quantitative specialist here at Statistics Solutions. I do see some familiar names, which is great. Welcome back to our webinars. Last week, we covered t-tests and looking at differences. Today, we're going to look at correlations. So how to conduct and interpret correlation tests. So that's more if you're looking at associations as opposed to differences. I'm going to go through the entire presentation first, and if you have any questions, you can type them into the chat box or the Q&A box, and we will do a Q&A session at the end. We will also send everyone a copy of the PowerPoint and the webinar. My colleague Sierra is going to put some hyperlinks in the chat box for scheduling consultations and checking out our free dissertation resources. So first, I'll give an overview of what we provide at our company. And we'll look at correlation analyses. What is the best type of correlation to run given your data? And we'll run some data in SPSS to illustrate, and then we'll conclude with a summary. So Statistics Solutions is our company, and we assist with every part of the dissertation journey, starting with topic development and prospectus and concept papers, and going all the way into the actual dissertation. So the intro through the methodology and then the results and the discussion. So we have methodologists, both quantitative and qualitative, and we have literature review specialists. So if you've hit a roadblock, just let us know and we can definitely help you out. You know, if you need help framing your research questions or picking a theoretical framework, or maybe you have some feedback from your committee that's just, you've tried submitting it multiple times, but you can't get it through. That's something, that's something we can help assist with. We also can help you with IRB forms and data entry templates. We have a SurveyMonkey account at our company, so we can help host a survey. If you just send us your data and your research questions, we can crunch the numbers for you and present it in a write-up. Then we assist with the discussion chapter and PowerPoints for defense, both proposal and final defense, and then we can help turn your dissertation and condense it down into a journal publication. So if you have any questions, just let us know. You can give us a call at 727-442-4290, or you can use the hyperlink that Sierra provided in the chat box. So we're looking at correlations today. I think it's important to first lay the foundation down for what is a parametric test and what's a non-parametric test. Parametric statistics are typically based on assumptions about the data and the population from which the sample was derived. And usually this assumption is that your data follows a normal bell-shaped curve for a distribution. That encompasses piercing correlations, ANOVAs, regressions. Usually if you have a continuous variable, the goal can be to run parametric analyses. Non-parametric techniques do not have such strict assumptions, meaning the data doesn't have to follow a bell-shaped curve. And non-parametric techniques typically involve ordinal data or nominal level data. We'll take a look at these different continuous, ordinal, and nominal data and kind of examples to look for that. But also the idea is if you are proposing a parametric technique and normality is not supported, many times you can shift to a non-parametric alternative instead, and we'll take a look at some examples. So more on the normality assumption, if you joined us last week, it's very similar. So basically, parametric statistics require, or one of the prerequisites is to have a bell-shaped curve for the data. And there are many ways to check for normality. You can use objective tests like a Shapiro-Wilk or Kolmogorov-Smirnov test, where it gives you a p-value and it tells you, are the data following a bell-shaped curve or are they deviating from a bell-shaped distribution? You can also look at skewness and kurtosis statistics, and you can look at scatter plots and histograms. I think scatter plots and histograms are valid, but they're more subjective. Everybody's going to interpret the scatter plot and histogram a little bit differently. So I tend to steer towards Shapiro-Wilk and Kolmogorov-Smirnov tests. If the data don't follow a normal distribution, then you can consider running a non-parametric alternative. And if you have a really large sample size, you can apply the central limit theorem to justify proceeding with parametric techniques, even if normality is violated. I put the citation here. Howell in 2013 states that violations of normality are not problematic when your sample size consists of exactly or at least 50 cases. So the central limit theorem basically states that the larger your sample size is, the more it tends to approximate towards normality. Okay, we have three different variable types or variable measurements. We have continuous, nominal, and ordinal. It's really important to understand these because based on the level of measurement for your variable, you can pinpoint a specific analysis to run. So for continuous variables, it has the word continuum in there. It's a variable that falls on a continuum or an interval or its ratio. Examples of these are test scores, temperature, weight, or composite scores from a Likert scale survey. So basically, if you have a lot of numbers as possibilities, or if you have decimals as possibilities, your variable is most likely continuous. Nominal variables are categorical, so variables that fall into distinct categories, but do not have an intrinsic order. So examples of this are gender, ethnicity, passing or failing of an exam. People will fall into one distinct category for most of these. A lot of demographics are nominal. Then we have ordinal variables, which are a subset of nominal. And you can see the word order is in there. So you do have an ordered or ranked category. Something like education could be considered ordinal, where it goes up a hierarchy or up a ladder. You could also have a Likert scale survey question. If you have one Likert scale survey question from strongly disagree to strongly agree, then that is considered ordinal as well. Okay, so we have 4 different types of correlations. We have 2 parametric and 2 non-parametric. Pearson correlations are used when you're testing the relationship between 2 continuous variables. Point by serial is used when you have a dichotomous variable, also called a binary variable, and a continuous variable. And then we shift to non-parametric techniques. Spearman correlation is used when you have 2 variables, when at least one is measured ordinally. Chi-square is used when you have 2 nominal level variables. So let's go back to the slide here. So basically, if you have 2 continuous variables, you do Pearson correlations. If you have a continuous and an ordinal variable, then you do a Spearman correlation. If you have a continuous and a binary, like passing and failing an exam, you do a point by serial correlation. And if you have 2 categorical or 2 nominal variables, like if you were testing between gender and ethnicity, or gender and passing and failing of an exam, that is when you can do a chi-square. All right, so when you run correlations, there are several things to pinpoint. You first want to look at the p-value, which applies to most statistics. The p-value tells you if you have a significant association or not. And usually that is evaluated at a p-value being below 0.05, unless you're running Bonferroni adjustments. Then you want to interpret the strength of the correlation coefficient. So we have a citation here in which Cohen states that if a correlation is between 0.1 and 0.29, you have a small association. Coefficients between 0.3 and 0.49 are a medium or a moderate association, and anything above a 0.5 is large or a strong relationship. So really there are three things. I did miss something on this slide. So you look for the p-value. Is it significant or not? You interpret the strength of the correlation coefficient. And then the third thing is interpreting the directionality. Is it a positive correlation or a negative correlation? Okay, so for a Pearson correlation, again, this is considered a parametric test, and it's used when you have two continuous variables. So the first thing you want to do is check for the assumption of normality. And if it's violated, then you might want to run a Spearman correlation as a backup, or potentially as an alternative altogether. That depends on your committee. They might say just disregard the Pearson correlation and go with the Spearman correlation. I tend to go with it as a backup. So I would still run a Pearson correlation and then report the Spearman as a backup to confirm the findings. If your sample size is large, then it's often acceptable to proceed with a Pearson correlation. We have the sample data set right here. And if you've joined us before in the previous months, you've probably seen this one before. So we have in SPSS here, each row represents a different car model, and the columns represent different statistics for these cars, mileage, horsepower, transmission type, weight of the car, and so forth. So we have a combination of continuous variables. That's anything with a ruler here. Anything that has a ruler is scale or continuous. We have nominal variables, which are things like this, distinct groups or categories. It has a little character A there. So engine type, if it is V-shaped or straight engine, and transmission type, if it's automatic or manual. And then we also have ordinal. So what I did here is to illustrate an ordinal variable. We have mileage, and if I sort mileage in order, right next to it, this is an ordinal designation for mileage. So the way I've coded it is 10 to 14.9 is going to be a 1, 15 to 19.9 is a 2, 20 to 24.9 is a 3, and 25 plus is a 4. This is how you can convert a continuous variable to an ordinal variable, putting the continuous values into categories, into ranked categories. And then you can define those categories right here in variable view. So 1, 2, 3, 4, you can see the different cutoffs. So hypothetically, if we were to run a Pearson correlation between the weight of the car, and this is in metric tons, and the mileage, you could do a Pearson correlation to ask, as weight increases, what happens to mileage? Does it increase or tend to decrease? So the first thing I would do is check for normality. And to do that, you go to Analyze and Descriptive Statistics and Explore. Then we'll put in mileage and weight over here. Then you want to check mark this box, plots. And we are going to select this option right here, normality plots with tests. Then click OK. And this is what it presents. Okay, so we have this tests of normality, and you'll have to check with your committee if they have a preference for what method to use, a Kolmogorov-Smirnov test or a Shapiro-Wilk test. This is a rare time in statistics where significance is actually not a good thing. It's not ideal. So these tests are comparing your data to a perfect L-shaped curve. And if you have significance, that means your data are significantly different than an L-shaped curve. So we're hoping for p-values greater than 0.05 on these tests. And we can see for weight, 0.142 and 0.093. Those are both greater than 0.05. So normality was supported for weight. However, for mileage, 0.033 and 0.008, those are below 0.05. So normality was not supported for mileage. So what I would do in this case is I would run a Pearson correlation, and then I would run a Spearman correlation as a backup. Okay, and to do this, we'll go to Analyze and Correlate, and then we'll do a bivariate test. And let's put in mileage, and let's put in weight. And you can see down here that the default option is a Pearson correlation. I'm not going to change that, but I'm also going to check mark Spearman. So we have our original plan and then our backup plan because normality was violated. All right, so this is what we see for the Pearson correlation. It's the top one here. The first thing you do is you interpret the significance. Okay, and significance is on this row right here. And the p-value is lower than 0.001, which is in turn lower than 0.05. So we do have a significant association between mileage and weight. Then you interpret the correlation coefficient. So I'm following these steps right here. Examine the p-value first, then interpret the correlation coefficient. And for this example, we can see that the coefficients are greater than 0.5 right here. So right in this table, 0.84, kind of disregarding the negative right now, 0.84 is larger than 0.5. We have a strong or large association between mileage and weight. Then we look at the directionality, which is the sign, and it's negative. So that means as mileage increases, the weight of the car tends to decrease, and vice versa is true as well. And the thing with correlations is there is no independent or dependent variable necessarily. You don't have to have independent dependent variables. You just need two variables of interest because it's a two-way association, not a one-way. So weight, as weight increases, mileage also tends to decrease, which intuitively makes sense. The heavier a car is, the lower the mileage will be. And then we have our backup below this. This is the Spearman correlation, and you interpret it the exact same way. We do have a significant correlation, and we have a correlation coefficient that is large or strong, and we have a negative relationship, so an inverse association. So I would probably do a scatter plot to depict this relationship, and to do this, you go to Graphs and Chart Builder, and then you'll select a scatter plot down here and click and drag a template to here. And let's put weight on the x-axis, and we'll put mileage on the y, and then click OK. What we have, we can clearly see that as weight increases, there tends to be a negative trend mileage. You can also put a summary regression line on this. If you go to, first you have to double click the graph, so double click, then go to Elements and select this option here, Fit Line at Total. And this is going to draw a summary regression line to depict the relationship. Clearly, it's negative. Okay, so that is a Pearson. We kind of did a Spearman here as well, but we'll cover that more in depth. A point by serial correlation. This is used when you have a binary or a dichotomous variable and a continuous variable. Because we do have a continuous variable in this analysis, you probably need to check for normality again. And if the assumption is not supported for normality, then you might want to run a Mann-Whitney U-test. So to run a point by serial, first we need to pinpoint a binary variable. And we have one right here, transmission type for a car. And this is automatic or manual. You have to recode. If you have it written out in words or letters, you have to recode to run a point by serial. You have to change it to numbers. So you could have 1 is automatic and 2 is manual. And then you can assign that designation here in variable view. 1 is automatic, 2 is manual. And it's very similar. I'm not going to check for assumptions again because we already did that, but we'll go to correlate and bivariate. And then we'll put in, okay, we'll keep mileage in there, but let's put in transmission type right here. And then we want to uncheck the Spearman correlation and keep a Pearson correlation check marked. When you do a Pearson correlation in SPSS with a binary variable, it is automatically doing the math for a point by serial correlation. There is no point by serial here, but it falls under the Pearson correlation family. Okay, and this is what we have. Interpret it the exact same way. You look at significance, which we do have a significant association. Then you look at the Pearson correlation coefficient, which is technically a point by serial coefficient, and it's 0.56. So comparing this to the citation right here, anything above a 0.5 is a large or strong association. And it's a positive coefficient. Okay, so for this, you have to look at how you coded a transmission. And it was 1 is automatic and 2 is manual. So this means that manual cars, because manual is the higher number here, it means that manual cars have higher mileage than automatic cars, which also intuitively makes sense. So as a follow-up to this test, you could run an independent t-test. If you go to compare means and do an independent sample t-test, and then put in mileage up here and transmission type down here. The purpose of this is to see the exact mileage for manual cars and the exact mileage for automatic cars. And we can see that right here by running a t-test. So for manual cars, the average mileage was 25.36 miles per gallon, and for automatic, it was 17.15. So that's why we said that manual cars tend to have higher mileage than automatic. Okay, we did Pearson, we did point by serial. We also have a Spearman correlation here, which we've already done an example of that. But to illustrate again, a Spearman is a non-parametric technique, first of all. So you don't have strict assumptions to verify like normality for this. However, if you propose a Pearson correlation and normality is not supported, then you might want to shift to a Spearman correlation. What did we do a Spearman on before? We did a Spearman on mileage and weight of the car, because mileage did not meet the normal distribution. But the more conventional time to use a Spearman correlation is when you have an ordinal variable. And we have one right here, which I described fairly early on in the presentation, is that mileage, we have a continuous mileage, but we also have an ordinal mileage. So this is often used when you have, if you're recording someone's age on a questionnaire, but you're not asking for their specific age, you have it cut off into multiple choice responses like 18 to 24, 25 to 30, 31 to 40, something like that. That's when you do Spearman's, because age is a multiple choice response as opposed to a specific value. So we could run the same test. We can do mileage. Let's do mileage with horsepower. So we'll go to analyze and correlate, then bivariate. And we'll put in the ordinal mileage, and we'll put in, we don't want to check mark Pearson here. because we don't propose a Pearson correlation with ordinal data, we propose a Spearman. And for this, it's very much like the previous one we saw. It's an inverse relationship. It's significant. It's a large association. This is greater than 0.5, and it's an inverse relation. So as mileage increases, horsepower tends to decrease. And then as horsepower increases, mileage tends to decrease. All right, and then we have one more examination here, which is a chi-square test of independence. This is used when you have two categorical factors and you're looking at the association between them. We do have two categorical factors here. We have engine type and we have transmission type. So if we were interested in, is there a relationship between engine type and transmission type, you can go to Analyze, then go to Non-Parametric Tests, then go to Legacy Dialogues. It's quite a few boxes. And then chi-square. This is one way to do it. There's even an easier way. If you go to Analyze Descriptive Statistics and crosstabs, I think this is the easier way. So Analyze Descriptives, crosstabs. And then you can put in engine type and transmission type. So you put one variable in the row box and you put a second variable in the column box. Then you go to statistics. Not sure where that menu popped up. Oh, here it is. And then once you click statistics, you want to check mark this option right here, chi-square test. And that's pretty much it. So you'll click OK. And this is going to present a cross tabulation. Okay, a cross tabulation is showing two categorical variables and what the frequencies are of people or of units that fall into both categories. So we can see right here, there are 7 car models that were automatic and straight engine. There were 12 car models that were automatic and V-shaped. Then you have manual cars over here. So you want to interpret down here the Pearson chi-square test. And it's 0.341, which tells us that we do not have a significant association between transmission type and engine type. If it was significant, you would typically have one of these cells would be much larger or much smaller than the other. But we don't have that. It's fairly dispersed evenly. So we don't have a significant relationship here. All right, so in summary, you want to pinpoint first your research questions, but then you want to know the level of measurement for your variables. Are they continuous? Are they nominal? Or are they ordinal? Depending on the level of measurement, there is a specific test you can run. And if the assumptions are violated, then you can shift to a non-parametric technique, or you can justify proceeding if you have a very large sample size. That is the central limit. All right, if we have any questions, you can type them into the chat box. It looks like we have some Q&A. Let me move these to a Word document. Okay, first question from JP. I have 2 groups, one that has a normal distribution and one that does not. Does that mean I have to go with parametric tests for both groups? I'm assuming you meant non-parametric here, potentially. It depends what analysis you're running. I'm not exactly sure what test you proposed. If it's correlations, then you could probably run parametric tests for the group that met a normal distribution, and then non-parametric for the other. I tend to run both. I would maybe run parametric analyses for both groups, and then because normality was not supported, then run non-parametrics for both groups. Kind of follow the same procedures for both groups. You don't want to run completely different tests. Okay, does that make sense? Right, we have a question from Megan. I used a Likert scale, strongly agree to strongly disagree. When I uploaded the data into SPSS, I coded it in numeric format, 5, 4, 3, 2, 1. This is ordinal for Spearman correlation. Yes, if you're looking at individual Likert scale questions, then it is ordinal. Then you should run Spearman's. However, if you're combining Likert scale items together, say you have 10 items that use a Likert scale and you're taking an average or you're taking a sum across those items, that resulting variable is continuous. So you could run Pearson correlations if you're building a composite score from your Likert scale questions. But if you're looking at an individual item, then you should treat it as ordinally and then do Spearman's. So that does sound accurate. Okay, we have a question from Jerry. How can you develop a mathematical model, linearity, regression, simplex model for research? It comes down to having hypotheses. So you need to have a hypothesized model if that's built on the literature in your topic or prior research. It's kind of difficult to just build a model randomly. You need to have some prerequisite, or you need to have some data that gives you an idea of what the model should look like. But yeah, once you have your hypotheses built, you need to identify your independent variables and your dependent variables, and then build research questions. So it's basically, for regressions and predicting, and typically a research question will say, is there a significant predictive relationship in X and Y? And X could be one independent variable, it could be multiple independent variables, and Y is your dependent. So you have to pinpoint all your independent predictors and then your outcome. Okay. All right, question from John. Can ordinal data be interval? And if so, can the latter then be run parametric? If you can find citations to support that online, I tend to fall into the other group where I think ordinal data are ordinal, and you should run non-parametric tests with them. But that's been a debate for many, many years. There are articles that support the idea that ordinal data are interval, especially if there are many categories. If you have at least 5 to 7 categories that are Likert scale, it can be treated as interval. I tend not to go in that direction, but you certainly can. And there are countless articles that will. All right, do we have any other questions? From Maddie. When can I use a linear regression or a logistic regression? We've done webinars on this in the past on regressions, but linear regression is used when your variable of interest, let me do some bullet points here. The linear regression used when your dependent variable or your outcome is continuous. Statistic regression used when your dependent variable, your outcome is nominal. Okay, so if you have a numeric outcome or something that has decimals, then you can do a linear regression. If you're trying to predict a categorical outcome, whether that's like passing or failing an exam, or predicting a variable that has 3 or more categories, then you can do a logistic regression. There are many types of logistic regression, so that's something to keep in mind. You have binary logistic, you have ordinal logistic, and you have multinomial logistic. Okay, so binary logistic is used when you're predicting a binary outcome. Ordinal is used when you're predicting a ordinal outcome, and then multinomial is if you're predicting a categorical variable with 3 or more groups, like ethnicity, for instance. You're trying to predict ethnicity, then you can use a multinomial logistic regression. I misspelled that here, multinomial. Yep. Okay. A follow-up question from Maddie. When is a nonlinear regression? That's actually not something I'm too familiar with. I think logistic regression falls into that family. You know, logistic is not technically nonlinear, or it's not technically linear. So I think this falls into nonlinear approaches, but there are many different types of regressions, Poisson regressions, and all of these different types of logistic regressions. So I think that these fall into nonlinear. And yes, we will send a recording of the presentation as well. Okay, question from John. Can hierarchical regression analysis be used with 3 IVs and 1 DVs? All surveys, ordinal, interval. Yeah, you can run a hierarchical regression case like this. So to do a hierarchical regression, you go to regression and then linear. And then it's about putting your predictors in steps. So just to illustrate here, if we're trying to predict mileage, you could put horsepower in the first step, and then you click next right here. And then you could put in weight as the next factor, and then click next, and then put in displacement. That's a hierarchical regression, is putting the predictors in steps and then clicking OK. And you basically get 3 regression models out of that. So you're trying to see, does the model improve with each additional predictor that you're including? So horsepower, then horsepower and weight, then horsepower, weight, and displacement. But yeah, I certainly think you can do that as well. If you have 3 IVs and 1 DV, you'll just have to decide when the IVs are getting entered, if it's in the first step, second step. How many steps do you have altogether? Those are all questions to ask. Yeah, you're welcome. All right, do we have any other questions? All right, we will send everyone a copy of the webinar and the PowerPoint. Come check us again if you have any questions, and just to show you where you can check for future webinars. Just in case, because I did see some questions about regressions, and we've definitely done that in the past. So down here, this was back in December, and this is our company website. If you click webinars and the webinar archive, this will show you the past webinars we've done. So we have done one on regressions, and I go into depth more about when to run certain regression models. So you can check that out as well. All right, let us know if you have any questions, and have a great day. Take care.